Basically, we have communication is transmitting a signal, whether it's audio or video, S of t, from A to B. So the main blocks are, it's a transmitter. Then the information goes through the channel, and then you receive the signal. There is a so whatever you receive, I'm going to call it R of t. So what you transmit, it could be S of t, but because of the channel, and there is also noise, right? That could be part of the channel or otherwise. So whatever you receive, we will write it differently from the. So you need to process it. So then there should be a receiver, and hopefully at the end of the receiver you will recover some signal, and we want this to be as close to original transmitted signal. So the whole task in this class is to study mechanisms to do all this. So we will go through each one of these blocks, but the ultimate goal is whatever comes out of the receiver should be as close to what was the original signal. So the original signal may not be what gets transmitted here. So the original signal could be f of t, and this could be s of t, because and then what you recover is, let's say, f hat of t, and you want that to be. So especially think of audio, right? So if this is some music, we do. So the transmitter may have different stages, and then ultimately you transmit something which is friendly or which can go through the channel. As you know, audio, for example, can only, if you just talk, it can only go so much. So if you want to send it to hundreds of miles away, then it has to be, something has to be done to that signal. So that's the whole job of the transmitter. So we will accept the channel. Except the channel, we'll be studying about both the transmitter and the receiver aspects. So man-made signal, generally we are interested in audio and video and also signals. And so we need to look at the signal properties and see what needs to be exploited, what is the structure of the signal. And that's where the next class onwards, in other words, the frequency characteristics of the signal, that's where a topic called Fourier transforms will come in. So this is a time representation. So the question is, what is the frequency representation? Frequency is in omega of the signal f of t. So for example, if you find out that whatever it is, we'll discuss this next week. So if the signal Fourier frequency domain, if it is dominant in this region, omega 1 to omega 2, then you know this is the region where the signal is present. And so this information are one and the same, because it's just looking at same thing in two different domains. This is in time domain, that's in the frequency domain. So we will, so the next next week we will go through the Fourier transform properties, and I will do a decent job, and you also should do a decent job, because this will help you in the graduate classes also. This is not something which you just use here. So there we will see that most of the man-made signals have this property. In other words, the information is limited. So this around the low band. So this is frequency low because around 0. So between audio and video, the only difference is how far the wave. So audio, for example, the information is spread till about 20 kilohertz, which you can't see from here in time domain. For video, that's about 3, 4, or 5 megahertz, depending on how far you want to go. So there the information is done like this. So all these signals that we are interested, fortunately, are band limited signals. So a band limited signal is where so remember, I haven't discussed the frequency representation. We will do it. When you look at the signal in the frequency domain, the information, unlike here, things go on forever, the talks, right? So whereas in the frequency domain, it is compact. There is nothing beyond a certain frequency. So a band limited signal is where f omega is 0 beyond a certain frequency, omega greater than omega naught. So this is your omega naught. Beyond omega naught, there is no information. So for such a signals, this is band limited signal. So that we will see once you study the Fourier transforms. For such signals, there is an important theorem by Nyquist. So this is the most quoted result in electrical engineering. So if you that such signals, if you sample at a certain, if you only take the samples, so these are the samples. I'm going to call it FKT. So what is this capital T? Capital T is this duration, sampling interval. One over T is the sampling frequency. So that I'm just saying some results qualitatively today. All this we will prove later as we go along. So what is Nyquist theorem? Nyquist figured out that so long, if for band limited signals, you can just get away with samples. You don't need the continuous information. Continuous information is as good as the FT can be recovered from So I hope you understand what I wrote, right? FT is the continuous signal, the black signal, can be recovered from these samples. These FKT are the green ones. Look at FKT, that's very sparse, here and there. I mean, of course, I'm sampling it periodically. So naturally, you may be thinking, how do you recover this from this? As I said, I will show you the proof. We will go through all this in when we finish the Fourier, towards the end of the Fourier transforms. So then the logic is, if you can get away with the green, why transmit the black? And this is the beginning of digital signal processing. That means these discrete values are enough to be transmitted. You don't have to transmit the continuous signal. But these discrete values could be, for example, this value could be 5.321. This value could be 4.8695. There is no end to all this accuracy, right? So in other words, if this signal goes from +5 to -5, any one of these discrete values could take how many values? In principle? Infinite number of values, because the value could be between 0 and 1, there are infinite values. Between -5 and 5, there are. So these discrete values could take infinite values. But so the next step is, since tinier, because you want to transmit it, another step is to so-called quantization. So this thing here has a sampler. So you transmit FT. FT becomes FKT. So now I'm talking about the transmitter. The first stage is a sampler. So FT becomes FKT. And because this has infinite values, we pass it through a quantizer. So a quantizer is like this, right? The X value is what is coming in. So a quantizer will look like this. So the meaning is, if ft is anywhere here, you just stick it to one value. So let me write down an equation. For example, let me show you a two-step quantizer. So this is a two-step quantizer. If a signal is positive, look at here. This is ft. This two-step quantizer means if the signal is positive, you take plus one value. And if the signal is negative, a minus one value. So a two-step quantizer, I'll draw it in green. Like this, right? So this is the quantized output. This is the black is the original signal. So the quantized output is a crude, CRUDE, crude representation of the original signal. Remember, originally here we only have the samples, but each of the samples could be anywhere from -5 to +5. So instead we could, making this little more refined, we could say so this is a four-step quantizer because look at the output. I have 1, 2, 3, 4 values. So how does this work? If a signal is, this is your, if ykt, what did I call fkt, if the input is between, this is the input, fkt, sampled value, and this is the output, quantized value. So I'm going to put it as f hat of kt. So look at it, output only has 4 values. So if the input is between here and here, you will assign it to this value. Let me call this y1, y2, y3, y4. So what is the algorithm? Algorithm is, so here you have 0, x1, then everything beyond x1. This is x2, everything beyond. So you can see if input is between 0 and this is, if the input, look at here, if the input is between 0 and x1, what will be the output? Anybody? What did you say? Yeah, you can assign it as y3, exactly, right. And if the input is beyond x1, y4, exactly, right. Y hat, f hat of kt is y4, just to, and you can see if the input is between this and this, it will be y1. If it goes, so if the input is so x2 is of course negative, this will be y2, and if fkt is less than x2, then the output will be y1, right? So these are 4 levels, 4 values at the output. Look at look at what is happening here. This.
What if the input is 0?
Yeah, so that's a good point. So that you can, by design, you associate, I should have written, you associate it with either this side or this side. So for example, to include 0, you could say if it is greater than or equal to 0. Since you are assigning, so all the values are covered. So for example, if x1 happens to be, so generally, even if look at here, if a signal is varying like this, if this is your input, you know that usually it stays between, this is 1 volt, this is 5 volts. Whereas if we may have another signal which goes like this. So you can see you may have to use different quantizations, but let me just finish talking about this. So here the input which takes all infinite values between -5 and +5 is quantized to 4 values. You can quantize it to 8 values. You can quantize it to 16 values. you can quantize it to 256 values. So that's only in the detail, but that's what we mean by a quantizer. So what is the advantage in quantizing it? If there are only 4 values, you can use binary representation. How many bits do you need to represent the 4 values? 2, right? Whereas if it is 2 levels, you need 1 bit. You can say this is associated with the 0, this is associated with the 1. So if you have 4 values, then this output can be transmitted using 2 bits. So you could say this is 0, 0, 0, 1, 1, 0, 1, 1. So if I have a quantizer which is 256 values, what is it? 256 is 2 raised to 8, right? Or 10? 8, right? So you can, so that will be a finer quantizer. And then you can, but the information, or in other words, this 1 green value can be transmitted using 8 bits. But if you want a little more refined one, use 10 bits, whatever, 1026, I think, right? Or 16-bit quantizer, that's where, so it comes up. But so you say, why not use the 32-bit quantizer? But you will have to see that, so one of this green will correspond to an, if it is 8-bit, a string like this. So this, so you can't transmit a 0, so something needs to be, so I'm going to come, so that's a quantizer. So then there also a lot of things are involved. Do you want a quantizer which is equal steps at the output, or do you want a quantizer? Look at here, I put how do you decide this point, x1, x2, x3, etc. So we will study about the quantizer also, how to design a quantizer. So there is job to be done here also. Several questions. How many steps should be there? 256 or 16 or 32? How do you decide that? Once you decide that, where do you do these breakpoints? And also, as you can see here, if a signal is squiggles too much around the origin, you may want to have more quantizing steps in this region. Whereas this signal, it may not be that important. So we will go, so quantizer itself, there are hundreds of papers on that, so we'll go over some aspects of that. But whatever it is, you decide, you see the advantage. If you come up with a 256 step quantizer, for every green value, it can be transmitted using, can be represented using 8 in a 8-bit binary representation. So that means whether it is your audio or my audio or video signal, ultimately all the information can be converted into strings of zeros and ones. Then so that's the quantizer. Then the question after the quantizer, so let me write this as f hat of kt. Then we will use a code book, CODE, code book, to convert this into these actual values into ones and zeros. So you may have your own local code book. So I'll call it a coder. So at this point it is like this. It's a bunch of strings and zeros. But if you know that this many bits, L bits, whatever, corresponds to one of this information. Remember, information is coming sequentially. After one sample, the next sample is coming after t seconds here, sampling time. So when we do the Nyquist theorem, we will see what is the best value for t, etc. So since the next information will come after t seconds, it is pretty clear that this need to be transmitted in t seconds. All these bits, that's the problem. So if you put too many bits, each bit will get how much time? If you have L bits, each bit need to be transmitted in how much time? T over L, right? Is that what you said? No. What were you trying to say? Hello?
So yeah, I was wondering how you said the quantizer encoder, how it relates to the diagram level.
So is it clear? I just so if the sampler is sample to sample is t seconds, right? And so if you each sample corresponds to L bits, then each bit need to be transmitted. So the bit duration TB is going to be T over L. Yes?
I'm also asking like the steps, like what you say. Is it everything between the sampler and the encoder, is it within the transmitter?
Yeah. So all this is part of the transmitter. Transmitter has, so look at this logically. A audio signal comes in, audio signal comes in, you sample it, at what rate, etc. we will go over that. So I'm just giving you an overview. Once you sample, these samples are quantized. Once you quantize, there are only L levels, right? I'm sorry, whatever, 256, call it N levels. So this may be an N level quantizer. So let me write it inside a little more neatly. Hang on. So this is an N which can be written, all right, N equal to 2 to the power L level quantizer. So you will choose N to be convenient of the form 2 to the power L. That's why I said 256, L will be 8, 512, L will be 9, 1024, L will be 10, etc. So then you get an L bits for one sample. That means each bit duration is only T over L. All right, now comes so that's, as I said, 0 cannot be just transmitted as 0, or 1 cannot be transmitted as 1. So you need another unit called the modulator. So we will study about this also. This is where you might have heard the terms amplitude modulation, phase modulation, etc. So that's where, so the modulation is a scheme where you, so if I call these bits AI, look at here, I'm just going to call it AI, A1, A2, etc. the bits. Right? So you can see at this point we have made it insensitive to whether it's audio, video, data, everything is zeros and ones. Then we may have a scheme where you will say 0 will be transmitted by some waveform S0T, 1 will be transmitted by S1 of T, for example. So all these blocks we will study after the Fourier transform. So the transmitter consists of sampler, quantizer, coder, and a modulator. Modulator is could be amplitude modulation or phase modulation, etc. So each of these aspects, each of these blocks we will go through. And then the signal is, so the idea of the modulator is to make it so that the signal passes through the channel, whatever is the channel, fiber or free space. Depending on that, the modulator will be designed appropriately. And then the best the channel will do is do nothing to the signal. Like in free space, if you transmit something from the Hubble telescope, the signal comes more or less uninterrupted here, except for the ionosphere and so on, right? So an ideal channel does nothing to the signal. But the channel itself could be, like as I said, ionosphere or etc. could be a stochastic medium. And we will not go into any of that. So the signal, as far as we are concerned, it is an ideal channel. Signal comes as it is, except there is always noise at the receiver. So the best model we will look at it is signal plus noise, whatever you transmit. In other words, you may be transmitting a scheme like this. So this is 1011. This is what you transmit. And if you, but what you receive could be something like this. So that's the because of the noise, right? But if the noise is too much, this may look like this. Then it will be very hard to see even with, so the whole point of the receiver is from the distorted signal RFT, how do you recover the original signal, whatever was transmitted. If ST was transmitted, then you want to recover something. This recovered thing should be as close to what it was transmitted. So how do you design this receiver? So this is also our job, receiver design. And we will go over this, and definitely over parts of various modulation aspects. So this is the big picture of the class. So a lot of topics to be covered. I'll go ahead. You can see it's amazing that we'll get to. So you will get a good overview and with a decent in-depth analysis. So if you don't have any other question, I'm going to erase all this and go into the.
So the center to modulator is within the transmitter.
Yes. Sample through quantizer, coder, and modulator. So you see the physical picture, right? All this is still at this side where you haven't come to the. So modulator output goes to the channel. This could be, if it is, it could be a microwave modulator. For broadcasting, it is AM, FM, etc. For communication, through the cell stations. So you have different cell stations. Again, depending on the, it could be in, yeah.
Can you remind me of the request of?
Yeah, so Nyquist theorem is, we will, as I was saying, the Nyquist theorem, he is the one who first figured out that most of the man-made signals, audio or video, in the frequency domain is band limited. In other words, all the information is centered around the origin. It extends to some point. For example, you might have heard audio goes up to, most of our audio goes up to 4 kilohertz, etc., especially somebody like me. But singers, etc., may go up to 20 kilohertz, but nothing beyond that, 22 kilohertz or something. Same thing with video, 4-5 megahertz. So for such signals, the original continuous signal, analog signal, can be recovered from its samples. Samples are enough. Then you quantize the samples to make it discrete values. Then the discrete values, you assign a code so that at that point everything becomes 0, 1, 0, 1, 0, 1. Then you transmit the 0, 1 using some waveforms. So that's the first half of the picture, more or less by midterm. Then after that, I'll concentrate on. So you can see this is by here already discrete signal. These are discrete signals, and here by this time it's only already digital signals because the information is only either 0 or 1. Irrespective of the underlying signal. The actual signal may be audio or video or different audios, etc. So the first topic is something you may have, some of you may be familiar with, called the study of the periodic signals, because most often, what is the most elementary periodic signal? Anyone?
Sine and cosine.
Yeah, sine and cosine, exactly right. So, so we want most often, especially when we go to for frequency modulation, etc., we'll be studying using, because it is quite complicated, again, using this, what if you modulate using a cosine waveform, etc. So this whole topic for this week is called Fourier series. So I'm going to show you the theory, why we do this, and do a couple of examples. Then you just do the homework and then do the lab work. So as he said, the simplest periodic signal is a sine waveform or a cosine waveform. Sine goes like this, right? So it repeats, right? You can see this is called the period. because after that, so what is a periodic signal? Any signal with this property. If a signal is the same if you shift it by some multiple of capital T. Capital T is called the period. So this is, for example, sine omega naught t. So you can see sine is 0 here. At 2 pi it is 0. So this point must be here. This whole thing is equal to 2 pi. So when you hit this point, it will be 2 pi over omega naught. T will be 2 pi over omega naught. But cosine will start from here. But in general, so we can generalize that concept. For example, so here you can see this information, I sort of repeats, right? This is not a good picture. Let me see it again. So this information, you write it in such a way that this keeps repeating. So here you can see that this is the period. Anything from anywhere to anywhere, from here up to here, this information keeps changing. So this is the period, or this is also the period. So what is the definition of the period? Period is such that ft, and if you push the signal any value, let's say this value, if you push it by t, you come back to the same value. That's just t. Or multiples of capital T. That capital T is known as the period. So this is called a periodic signal. So the simplest and the neatest periodic signal is this waveform. But it doesn't, see, these are all periodic signals. Let me give you some nice examples. Anybody, what is the period here? Let's say this is on for A, and then it is off for some time, and this is again. So this is 1. So what about this signal? What's the period? Anybody? It repeats. So obviously, the way I wrote it, this information gets repeated. So T is the period, not A, right? So this is A. So A is, this signal is such that it is 0 when T is less than minus A by 2. So in this duration, right? And then other, not 0, it is A during that time and 0 otherwise. Within T. And on the other side also, and it repeats. This is another periodic signal. What do you call this waveform? Anybody? The one I just drawing. Very good. That's square wave. What's the period here? Let's say this point is A by 2. Anyone? What is the period?
2A.
So look at here. If you start from here, the information goes
3A over 2.
all right. So the way I wrote it right. So this is a period, right? So what he said is right. If this is a by 2, assuming this will be a, right? The positive portion is a, negative portion is a, 2a, not 3a by 2. That's the period, etc. And some periodic signals may have symmetry properties. Do you see any symmetry before I tell you what is the symmetry here, you see? Anybody? Do you even know what is symmetry? What is it?
F of t would be equivalent to f of negative t.
For this one. So what do you call such signals?
Evens.
Even. How about this? So for those of you who did not follow, there are also even and odd signals. Even signal has this property that value at some minus point is the same as the plus value. Look at here. If I take some value, if take to be this to be t naught, and if I come minus t naught, the values are the same. Look at here. If I take t naught to be this point, t naught, minus t naught is here. So here the value is plus, here the value is minus. So they are opposite. So even signals have this property, and odd signals have with a minus sign. F of minus t is, anybody? Minus of f of t. So but the signals I wrote there has that either it is odd or even, but periodic signal only need to have this property. So let me start with the important result for periodic signal. A very periodic signal So for every periodic signal, we know there is a period. That's very physical. Period is the duration from which the information repeats. And the fundamental frequency omega naught is defined as 2 pi over t. So 1 over t is a frequency, so that's a duration. So the Fourier's theorem is every signal has a discrete representation using its fundamental frequency. This is what he means. There is an amplitude, and if you, what is e raised to j theta? Anybody? Plus? So when I write e raised to j theta, this we will read it as a complex sinusoid, because a cosine part and a sine part with a j. J, what is j? No, what is the value of j? Square root of? Square root of -1. Everybody is clear? As I said, if somebody is not clear about something, please write to me. So you can think of this way, saying that look at what is being written. I will go over all the details. So any arbitrary, it's amazing, right? You don't see anything nice here. Even this signal can be written as a sum of sines and cosines with the different frequencies. But all frequencies are based on this fundamental frequency omega naught. So either k equal to 0 will be DC, k equal to 1 will give you omega naught, k equal to 2 omega naught, 3 omega naught, 4 omega naught, etc. So that's what this means. So the question is, what are the CKs? So say to find the CK, let's do this one, FT. The CKs are given by this quantity because you can easily see this. So if it is plus here, I put minus here, and now if I substitute this expression here, this comes 1 over t integral I'm going to substitute for ck e to the power j so 0 to t. Remember, integration is on t, so this is a constant that goes outside. So initially I will do a few things in detail. K goes from minus infinity to plus infinity, and integral e raised to j k minus n omega naught t dt. So what is the integral of, I shouldn't write, what is the integral of e to the power jx dx? Anybody?
1 over x times
1 over j.
1 over j
All right, what is on the numerator?
minus j times exponential
E raised to jx over j, right? So, right? So if you use that here, this will turn out to be 1 over t summation ck. This 1 over t, I'll put it here. Integral ck 1 over t e to the power j n minus k. First of all, if k equal to n, what happens to this integral? Just with k equal to n, this will be 1. Integral 0 to t, 1 will be t. Capital T divided by t is 1. So let's do this integral here. So if I do this, this will be e to the power j. Oh, first of all, if k equal to n, as I said, what is the value of this? K equal to n, this is 1, right? Because it goes like, if k equal to 1, this whole thing is e raised to 0, which is 1. So when you integrate, you get t, capital T divided by small t, it is 1. So the only thing we need to do is when k is not equal to n. When k is not equal to n, this is not a 0, so I can write this as e raised to j k minus n. So let me call, rather than carry this, let me call this to be m. E raised to j m omega naught t divided by j m omega naught, right? Now I need to substitute 0 and t. So anybody, when you substitute the top value, what do you get? Omega naught multiplied by capital T. Omega naught multiplied by capital T is 2 pi. So the top limit will be e to the power some multiples of 2 pi. How much is that? 1. So a few things you need to be clear. How much is this? So that is cos 2 pi, cos 2n pi plus j sine 2n pi. Cos 2n pi is how much? 1. So this is always 1. Yes? How about this? If you're not following me, don't sit there. You ask me why it is. Because this is cos 2n pi plus j sine 2n pi. Remember, this is always 0 because sine 0, sine 2 pi is 0, sine 4 pi is 0, etc. Cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1. So what he said is right. This is equal to 1. How about this?
minus 1 to the power of n.
What?
Minus 1 to the power.
Alright, so you guys may be too fast for others. Cos n pi plus j sine n pi. So So cos n pi, look at here. What about here? If n is sin pi is how much? Sin pi. So simple things you need to sort of come quickly. Sin 0, sin pi, sin 2 pi. So if you conclude that, then you will see that this whole thing is always 0. Here, cos 0 is
1.
cos pi minus 1. Cos 2 pi 1. So cos 3 pi minus 1, it will flip. So we can, as you said, you can write it like that. So look at here. Here omega naught, when you put the top limit, this will come omega naught capital T minus 1, because when you put 0 here, the whole thing goes to 0, so e raised to 1. So what is this value? We just went through this. This is 2 pi. So this whole thing will be, if m is not 0, this will be 1, right? We just wrote 1 minus 1 is 0. So this is a standard result which you should realize. E to the power j n t dt integral 0 to t 1 over t. Is 1 when n is 0, is 0 when n is. That's what I just proved.
Can you why when we're doing the integral are we doing k minus n and like changing it to m?
No reason except otherwise I will have to carry it over here as k minus 1 is just a number, right? It's just easier to write.
Yeah, so you wrote the Fourier like coefficients and use k. I don't understand why we subtract n when we do the integral.
All right, watch here. This is ft, right?
Yeah.
So I'm just computing this integral, because the whole question I asked you was what was ck.
Right.
So for that I said let me compute this number, see what happens.
Okay.
So here I put n, not k, because I just want to compute this.
Okay. That looks like a k to me.
All right, this is not k. So then you say when you complete, otherwise if I put k, this will become k minus k 0, right? And so here, because it was n there, when I plug it in here, this will become k minus n. Do you see that much? Now, but the integration is not on this, integration is here. So what is the moral of the story? Look at here. Moral here says this value of this integral is 1 when n equal to k, and it is 0 when n is not equal to k. Do you see that? All right, so if that is the case, look at this integral. What will be the value of, where did I go? So, okay, so we came here, we wanted to compute this. This integral will only make sense when k equal to n. This remember, I wanted to simplify this. So anybody, what will be the value of this whole thing? This whole thing is 1 when n is k, yes?
Yeah.
Because this integral, I computed it somewhere. Look at here. This you can call it m if you want. So this whole integral is 1 when n is k or when k is n. So bottom line is this will equal to what? Whatever we started computing here, this quantity will be equal to what? Anybody? On this summation, look, when k is n, this is 1. When k is not equal to n, there is no contribution. So this will turn out to be? Which term will have contribution from here? Cn, not C0. See, k goes all the values from minus infinity to, but when k hits n, this will be 1. So the question was, what is the value of ck? Here is the answer. ck is 1 over t, integral 0 to t, ft. This is what I wanted to prove. That's why I started with this. Look at what I have done. I put an n here. I went through all this. Showed that if you put n there, you get to Cn. You still not understanding why I did this? You?
So you just started with the answer for what CK was and
I don't know the answer, but I'm saying let me compute this integral. Let me compute this term. See, here I just wrote a CK, right? That's a constant. The question is, what is this constant? So I said, let me start computing this. When I computed this, that turned out to be Cn. Remember, n is just an index, so you can replace n by k, and that's your answer here. So what is the bottom line here? If ft has a representation, in general, any periodic signal can be written as sigma ck e raised to jk omega naught t. So the question is, these are the amplitude. This amplitude is given, of course, the amplitude has to be derived from the signal itself, right? The amplitude has to be derived from the signal. So it has something to do with the signal, and that's the relation. Now you see that, you can see that in general this amplitude will be complex because you have two parts, right? Integral ft. You can write this as cos k omega naught t minus j sine k omega naught t. So this will be cos k omega naught t So this, look at here, this is, I'm going to call this alpha k following the notes, and maybe ak, right? I don't remember, but it doesn't matter, you can. And this I'm going to call it bk. So all I have said so far is a periodic signal. Periodic signal means if ft can be written ft and it's a shifted, it's the same as its shifted version where you shift it by capital T, then it can be written in terms of cosines and sines involving a fundamental frequency and its multiples. So the multiples are called harmonics, 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 right? So so the question is, what is the meaning of, what is the physical interpretation of all these CKs, and how do you find them? How do you find the CKs? So obviously CK depends on FT. So you multiply by e raised to minus jkt and integrate over one period. Now, in the notes, maybe I'll do it next on Wednesday, let's see, but I want to get to some material today. In the notes, I also show that to find the C naught, you can integrate over any duration. So this proof is there in the notes, but I'll probably do this when we come back day after tomorrow. So if we put T naught equal to 0, it will be 0 to T. So let's just, so what are these AKs and BKs? So AK is 1 over T, 0 to T FT cos K omega naught T dt. And BK is 1 over T integral 0 to T FT sine K omega. All right, so if remember, ft doesn't have to be real, but if ft is real, ak will be what? Look at here, ak will be at least real, because ft is real, this is certainly real. If ft is real, AKs and BKs are real. Look at the examples I wrote here. So for these are real signals because you can see them, they are right in front of you. So for them the A case and B case are real. So any signal can be written in this form. And so I'm going to come to real signals, which is what mostly we are interested. But before that, let me show you a property of these signals. Okay, so pay attention here. What I'm doing is, you have two periodic signals. So both of them, look at the way, both of them have the same period. Two signals have, so to answer you, look, k is a dummy variable, so I can use k, I can use another variable also. It doesn't really matter, right? So they both are, these are the Fourier representation. How will you get the alpha case? You go like this. Alpha k is given by this expression, f1t e raised to minus j. Look here, right? Alpha k is f1t, this expression. And beta k will be, you put f2t here, that's all right. So let's look at this inner product. So look at what, before you write, look at what I'm doing. I'm multiplying f1 and f2, except f2 I take the complex conjugate. Why am I doing all this? You will see in a minute. So I'm going to, look at here, I'm going to substitute these two expressions and do the integration. So integral sigma ck e raised to jk omega naught t. And this expression, second expression will be what? Anybody? Not ck, alpha k.
Beta.
Except remember, these could be complex. So because I have a complex conjugation here, its complex conjugation will be what? Complex conjugate here and minus here, complex conjugate there. So this will be beta n star e raised to minus j n omega naught t dt. So I'm going to do the, remember, integration on dt. So integration from 0 to t. So this will be one summation on k, one summation on n, alpha k, beta n star. Then you have 1 over t integral 0 to t e raised to j k minus n omega naught t dt. We went through this. What is the value of this integral?
1 if k equals n and 0 if k is not equal to n.
That's good. So look here, what will happen to this term? What she said is right. What she said is, I'll write it down here. This is 1 if k is equal to n, 0 if k is not equal to n. Now if you are wondering why this is true, you should go back and look at what we did a little earlier. So then what will happen here? This double summation will collapse to what? Anybody?
Alpha and beta, the product of alpha and beta.
Yeah, because this will only have values only when k equal to n, right? When k equal to n, this integral is 1. So this will simply reduce to sigma k from minus infinity to plus infinity, alpha k, beta k star. So this relation is an important relation. This is known as Parseval's rule. 1 over t integral 0 to t f1t f2 star t dt is sigma alpha k beta k star. I think this is Parseval's, not Bessel. All right, one or the other. Okay, so the most important thing is what happens if you put F1 equal to F2. Anybody? So I'm going to put F1 equal to F2 equal to, I'm simply going to call it Ft. So what do you get? This is absolute value squared dt, 1 over t. Here what do you get here? F1 is F2, so this becomes what?
Alpha k.
Alpha k?
Alpha k from times that conjugate to alpha k.
So number multiplied by conjugate is called what? But now I can write it to be f the values are c case, right? For ft it is c case. Alpha k role is played. So we have this relation. This is known as the Bessel I could be flipping these two, right? Anybody knows what is this quantity? If a signal is there, if you square it and integrate from 0 to t, what do you get?
Energy.
Energy, very good. So this is energy. Energy divided by the duration is?
Power.
Power, right. So this is the power of a periodic signal. So look at here what it says. The power of the periodic signal is distributed over these different frequencies. So you get this picture, whatever is the power, you have some power at DC, C0 squared at DC, at omega 1, this is corresponding to omega 1, so you have C1 squared, you have C2 squared at 2 omega naught, and at k omega naught, you have ck squared. And if you add, look at here, if you add all these things, you get the total power. So what must be these quantities? Anybody? This quantity must be what? If you add all these quantities, you get the total power. So each of this must be representing. I'll go over it one more time. Look at here. At frequency 0, you have this much. At frequency omega 1, you have this much. At frequency 2 omega naught, you have this much. If you add all this stuff, we just proved, look at here. If you add all this stuff, you get the total power. So each of this must be representing what?
Power at each frequency.
Yeah, power at those frequencies, right. So the moral of the story is a periodic signal, the total power is distributed at these specific frequencies and nothing in between. So that's what I wanted to tell you about. Because look at here, this gap, there is no power. This gap, there is no power. So for a period, so we can conclude that a periodic signal power is distributed at discrete frequencies, not any discrete frequency, at its fundamental frequency omega naught and its multiples. So I'll write a note here. That's a summary now. For periodic signals, total power there is some power at origin, then all the other powers are multiples of this frequency called omega naught. Omega naught we call the fundamental frequency, we already said. And you can conclude there is no power anywhere else. So power is discretely distributed for a periodic signal.
Is that also called the spectral density?
You can call if you want, you can use the word spectrum, right? But generally the power distribution. What is the energy of a periodic signal? Anybody? Let me see how much you can think. Energy of a periodic signal.
Without doing it.
Energy of a periodic signal. A periodic signal goes from where to where? Think about it. A periodic signal has to go from where to where? From where? It cannot. This cannot be a periodic signal, because then you go a little later. You can't have that. So a periodic signal must go forever. So what is its energy? So energy makes no sense, because energy is infinite. So what we do is look at what we took one period, we found the energy in it. That's the reason I divided by T. This is meaningful to talk about. But then what we found out was this power is distributed among few frequencies. So that's the story that we need to start with. I need to do an example, but let me do a little more. So we can do a little simplification for real signals. So most of your problems will be dealing with a real signal. Like here, some of this could be a homework problem, but I'll do this for you. So what is our job? To find out the C case. But let me show you a simplification. Remember, let's start from here. I'm saying Ft is real. If Ft is real, Ak will be real. And B case? Imagine just Bk without the J. Real, right? So Ak, which is 1 over T integral 0 to T Ft cos k omega naught T dt. This is real, because Ft is real, this is real. And Bk, which is 1 over T Okay, you have to pay attention here. I'm going to do a little bit manipulation here. Look here. I took the original expression. Now look here, Ck is here. Ck, so I'm going to substitute for Ck. You have to follow me. We know that this is real, so we should be able to get rid of all this complex stuff. So this is going to be summation Ak minus jbk. Why am I writing this? Because I have it here. Ck is Ak minus jbk multiplied by this quantity, which is cos k omega naught t plus j sine. Okay, you can do the multiplication. There will be some terms involving So what are these terms, the real terms? Look at here, Ak multiplied by cos, so Ak cos k omega naught t, and minus j bk multiplied by, so j multiplied by j is j squared, with minus sign, what do you get? Plus 1. So this is bk sine k omega naught t. That's this part. This will be Ak sine k omega naught t minus bk cos k omega. Look here, this is real. So what must be this term?
0.
So we can conclude that the right side must be real, so all those terms have to go to 0. If f of t is real, we have some simplification. Ft can be written as sigma ak cos k omega naught t. Okay, so everything is real because AKs are real, BKs are real. So if I give you an example, we need to find out AKs and BKs. That's your job. We'll put it into this example. But sometimes you have this two special cases. First one is ft real and even. So let's do this special case, which will be the case on the top. So even means f of minus t is, what is even? F of t, that's what the definition of even. Look at here. So what is f of minus t? Look at here. F of minus t is sigma ak cos minus k omega naught t plus sigma bk sine minus k omega naught t. So what is cosine of minus theta?
Cos K.
So this is cos k omega naught t, and here
Negative sine.
minus sine k omega naught t. You see that, right? But this is the same as f of minus t is the same as f of t because it's even. So add this plus this. What do you get? 2ft. What happens to the last term? This and this. And this adds up. 2, you get 2. So do you see this ft is yes? And I can simplify this further. When k equal to 0, what will be the value here? A0 plus summation. I'll write the positive frequencies. So ak cos k omega naught t plus summation ak k from minus 1 to k from minus 1, minus 2, minus 3, etc. Negative frequencies, ak. So this is the same as I can put minus here. These are, look here, negative frequencies. Here you have negative and positive. So we took care of the 0. Then these are positive frequencies. These are negative frequencies. So anybody, cosine of minus theta is? Cosine theta. What is a minus k? Let's look at here. You put minus here. That means we put minus here. So a minus k is?
Same as
So we have another result here. A minus k is the same as ak. When I'm here, let's also do b minus k. What is it? If I put minus k here, this k becomes minus k. Sine of minus theta is?
1 by pi.
So this is minus bk, right? So we need that little later. So look, a minus k is the same as ak. Essentially, this is same as this term. So we get the result a naught plus 2 summation ak u. So you can see it here. ak cos k so that's for real signals. If ft is real and even, then you only have ak's to find out. So let's say ft is real and odd. So think of this example, the last example. This is an odd signal. Sine is an odd function, right? So ft is real and odd means f of minus t is minus ft. So ft is real, you see, you only have the a terms. And that itself we can simplify to this. So all we need to figure out is the a0 and ak. Here let's see, ft is sigma ak cos k omega naught t plus bk. And B of minus K?
Minus.
Yeah, because look somewhere here, we did this, right? B of minus K is minus BK.
Because that's when it's even only, right?
No, here we're saying odd.
No, BK is, no, I mean, for any, if you just change K to minus K, look at here. K to minus K, this K will become minus K. Sine of minus K is minus sine. So B of minus K will be minus BK always, right? No, I'm sorry. You're not, hello, how come you're not fixing my mistake? Why should I write B of minus K here? There's no reason, right? We're just writing F of minus T. All I have to do is flip T to minus T. Right? T is not here, T is here. So this is good. This will be BK multiplied by this, right? Not B of minus K. BK multiplied by here, T is replied by minus T. Look at here, this is Ft. I am finding out F of minus T. So wherever T is there, I make it minus T. There is no T here, so there is a T here, I make it minus T. But sine of minus something is minus this. Okay, so this is good. Now subtract this from this. You know, the Ft minus Ft, if you subtract, what do you get? Right, the same as 2Ft. If you subtract this from this, the first term goes away. So you simply get BK. This minus this, but there is a minus sign. Minus minus becomes plus. Okay, so these are the negative frequencies. These are the positive. Here all the frequencies. What is the value of B0? Look at here. What is the value of B0? So put K equal to 0. B0 is always 0 for any signal. So B0 is gone. And we already figured out B of minus K is minus BK. And this is minus of sine K omega naught T. Minus minus becomes plus. So that is just twice. So it becomes 2 times summation BK sine. So if this is the moral of the story. If the signal is real and even, you only have A terms. If the signal is real and odd, you just have positive frequencies, but there is no 0 term because B0 is always 0. Omega 0, omega 2 omega 0, 3 omega 0, etc. But always the previous picture is true. In other words, for a omega 0, 2 omega 0, I mean, if there is a real signal, then it is A0 squared, A1 squared, etc. Whereas here, there is nothing, it only B1 squared, 0, omega 0, then something at B2 squared, etc. This will be the picture. Because look at here, frequencies are omega 0, 2 omega 0, 3 omega 0, etc., etc.
Shouldn't it be FT and not 2FT?
Right, 2 cancels, right. So FT is this. See, 2 will cancel, right? You don't see it? See, there is, this term is identically equal to this with the mic.
When you did ft minus negative ft, you get 2ft is equal to 2 summation.
Right, 2ft here should have been a 2.
Yeah.
That 2 will cancel. So ft is equal to this.
But you
Then,
keep 2 at the end.
no, I am getting late. This should be cancelled, right? These two cancel. Then let's say, since you said I pulled out B naught, I showed B naught is 0. Positive frequencies, negative frequencies. These terms are same as this. So you get 2 times this. This 2 will stay. Like here, there is a 2 here also. So let's take this example, the first one. Ft is like this. Remember, you can always write like this, ft equal to sigma, start from the first thing. So this is too complicated at this point because we know this signal is real and even. So we should use this formula. It's much make life very simple. So even though this is true, I know that this signal can be represented as this form. So only thing is what is AK. So somewhere we wrote, right? AK is, I took it off, but you have it there. What was it? FT. Now what will be the limits here?
0 to t.
So this is where I want you to go over a proof. I said you can integrate over any period. So we need to exploit the symmetry. Let's integrate from minus t by 2 to here. But the signal is 0 here and 0 here. So it's enough to integrate from minus a by 2 to a by 2. Look at here, this is even. This is even. An even signal even multiplied by even is? An even integral integrated over symmetric region is the same as? 2 times integral from 0 to t. So all this, so we can write it as 2 times the integral from 0 to t ft cos k omega. So this is the simplification. This is, so if you are careful, you only need to do the minimum work. So following or?
I'm a bit lost about the from 0 to t part.
Why? So remember, as I said, integration can be done from anywhere to anywhere. You can do from here to here. But you can also do from here to here, because that's something you are going to look through at home. I told you that you can do this integration from any t0 to t0 plus t. So I'm going to do from here to here over a period. But the signal is 0 here and here. So the actual integration is only from minus a by 2 to a by 2.
What's regarding the second one? 0 to t.
Oh, that's what you're lost, okay. So this should be a by 2. Is that what you, okay. And what is the value of the signal here? 0 to a by 2. Look at the picture. Whatever is this constant, so let's say cold one. So this will be 1. So now the integration is easy. What is the integral of that term? Anybody? What is the integral of cosine? Can't be. Divided by 2 over t. Yeah, you're right. I confused you. It should be 0 to a by 2. This is right?
Evaluated.
Yeah, 0 to a over 2. So this is 2 sine k omega naught minus sine 0 is 0 divided by k K. What is T omega naught? Omega naught is 2 pi over T. 2 pi, right? So this quantity is 2 pi. So this is 2 cancels. Now, do you know this? What is this? Anybody? Huh? So, when you draw it, it will go like this. So, this is a useful function. I'll talk about this more as we go along. Sinc x. Sinc x is sin x over x. Sine goes like this. Sine is like this, right? This is sin x. Look at the origin value. Sine 0 is 0. Sinc 0 is 1, right? Why is that? Because you can take the limit of using Lebesgue, L'Hospital's or whatever, right? In any case, if you want to write it in using sinc, so we multiply by omega naught a by 2 here. So we multiply by omega naught a by 2. So you can write this as omega naught a by 2 pi sinc k omega naught a by 2. That's the coefficient ak. So what will be a0? Sinc 0 is 1. So a0 is just this. Now remember, a has nothing to do with the t. Obviously a is, what is the relation between a and t? Just one relation, inequality. Anybody? What is the relation between a and t? Look at the picture. What must be true between a and t, I'm asking. Look at the picture. You have an issue?
I have a question regarding this one. When we're doing the definite integral, why didn't you take the 0 into consideration? Wouldn't it be 1?
B1? Yeah, what about it? Integration with respect to t.
Yeah, no.
So what is the relation between a and t? One mild inequality.
A is less than T.
Well, very good. A is less than t, right? Because otherwise this problem won't make any sense. So let's do a case a equal to t by 2. Let's see what this comes up. This is a special case. I think that's called half wave or something. Then what happens? A is t by 2. So what happens here? If you put t by 2, omega 2,
Omega 0 over 4.
this becomes pi, right? A is t by 2. Omega naught t is 2 pi. Divided by 2 is pi. It's 1 over 2, I think, right? K omega naught t by 4 divided by k. Omega naught t is 2 pi divided by, so this becomes, what is it? Sine pi by 2, right? Divided by, how much is this? Oh, 2 pi.
Omega 2 as well.
Okay, so now how about this? What is sine 0? K equal to, let's start, not k, k only goes from, 0, no, 1, 2, 3, etc., right? 0, we already took care of it.
Where, sorry? Where did we take care of K?
Somewhere here, right? We took care of A naught as, you forgot already? This is here, right? So A naught is, remember, K equal to 0, sinc 0 is 1, so A naught is simply omega naught a by 2. So in our case, if you put a equal to t by 2, it is 1 over pi, right? Or pi, so that's good. So k is now non-zero. When k is non-zero, k goes from 1, 2, 3, etc. So when k is 1, sine pi by 2 is? When k is 2? K is 3? Minus 1. So let's put odd numbers. Let's say k is 2m plus 1. Then what is the value of this? Anybody can tell me? Sine 2m plus 1 multiplied by pi by 2.
1 over 3.
Yes? Alright, so you can see how the simplifications go by. If anybody didn't understand, I will again, you look through it. Look at here. So you mentally go through k equal to 1, this is 0. Because sine 0, what? Sine pi, sine 0, 0, sine pi by 2, 1, sine pi 0. So you see odd values. Next value is minus 1. Sine 3 pi by 2 is minus 1. So if let me put this to be an odd number, 2m plus 1, then you figure out that when it's actually of the form minus 1 to the power m. And so because if m is 0, k is 1, you get 1, m equal to 0. So you get this special simplification, but at least you should bring it to this form.